Yeah, thanks to everyone for taking the time to be here. So what I'm really trying to do here is just to go through a lot of information to describe what it is you're testing when you're testing moisture in concrete. And that might sound a little a strange way to put it, but basically there's a number of test methods that have been developed over the years around the world. And it's important to go back to understand what it is you're testing when you're doing them, because they all provide some information that can be valuable if it's understood what you're testing. So what I'm going to do in today's presentation is to go through as some of the misconceptions and some of the confusion that's out there, so that at least people can get an understanding of what it is we're measuring. You mentioned, Chris, at the beginning, these different standards from ASTM. Well, there's also the Australian standards, there's the British standards, there's Scandinavian standards, there's German standards, and they've all been developed over many years. And so they all approach the same problem from a slightly different point of view. So what we're going to focus on today is the difference between measuring and testing moisture versus measuring and testing vapor in concrete, because both are used. In fact, you could take the whole world of all the standards for measuring moisture and you could divide it up between those that measure moisture and those that measure vapor. So the British standard and the Scandinavian standards are all vapor. The German standard, there's a few others as well that are moisture content. And then, with the carbide meter is a moisture content meter. The calcium chloride test, which is used a lot in the United States, is measurement of vapor. It's the measuring the rate of vapor coming out of the concrete. And you can do gravimetric testing, or even our meters are calibrated based on gravimetric testing. So that gives you an indication of the moisture content. And there are other meters as well that do something like that. So let me just try and change my slide. So this just so briefly, we're just going to go through the difference between RH and MC. So RH being relative humidity, MC being moisture content. Explain that vapor is not liquid moisture. Hydrostatic pressure is extremely rare. Vapor pressure transmission doesn't carry solids or salts. And then we're going to go through something of osmotic blistering and hydraulic pressure. And I see Clayton is here, Clayton Schull, and I also noticed that Bob Higgins is here. So it's a pretty amazing group, actually. So the problems that we see come from moisture, not from vapor. And vapor is used to gauge the moisture content. So that's something that people need to understand. In the United Kingdom, in the UK, they call the relative humidity testing, they call it ERH, and you can look this up, equilibrium relative humidity, ERH, not RH. It's known as ERH because you're trying to gauge the equilibrium between the vapor and the moisture in order to tell you what the moisture is. So there are issues with that, and Bob Higgins can speak to that. And there's other sort of, like any test method, there's always potential for false positives, a potential for false negatives. So the idea is to identify those false positives and false negatives so that when you then you can spot them and you can avoid them and you can reduce the issues. So we do that in our way of sort of trying to reduce the issues is to measure both the vapor and the moisture. So by measuring both, they should line up something along the lines of this chart that you see here in front of you, which is called a sorption isotherm. So what this shows you is the humidity at the bottom, the relative humidity. It goes, if you can see my pointer, it goes from 0% up to 100% relative humidity. And up the right-hand side, we see moisture content up to about 6%. Now, this is coming from Goran Hedenblad, who was responsible for much of the research that went into F2170. So this is from his presentation. And I think they use calcium carbide in for the moisture content. So I've done a conversion to gravimetric in this. So I'll just show you. But the point is, this chart goes from 0%. This is tracking the relationship between the relative humidity and the moisture content in the concrete. And there are two lines, and that's because of the alkalinity of the concrete. And this becomes really important as we get to the top of this chart. So as we get above 90% RH up at this end, we can see the difference. The moisture could be 4.5, or it could be over 6% moisture content. And that is critical. That is critical when you're using relative humidity to identify if the concrete is sufficiently dry. You have to be aware that you could have a lower RH number. You could have like a 93% RH number with over 6% moisture, whereas you could have a 99% moisture content or relative humidity, 99%, and you could have 4.5% moisture content. And this is key to understanding the relationship, because if you look at this 4.5% moisture content here compared to over 6% moisture content, that's your issue. That's where you're going to have big problems that you won't be able to identify with relative humidity testing alone. It's
Andrew, is it safe to say that around 4 to 4.5% on that scale, or the scale that your product uses, is safe for flooring products, for topping compounds?
Yes.
Well, that depends. Sorry, I have to interject here.
Please.
That depends on the adhesive that's being used. If you're dealing with an acrylic adhesive, or are you dealing with a urethane adhesive, or are you dealing with an epoxy adhesive?
Sure.
Yeah. So William has put a lot of this, and William, who just spoke there, has put a lot of this into practice. So he has developed moisture content for different products that they produce for different adhesives. And it's a lot simpler in a sense to point to moisture content than relative humidity. But the idea, our preference is to measure both. And the reason why we measure both is because we want to understand the alkalinity of the concrete, and we want to get a good indication of that a high relative humidity is actually a good thing for concrete. And this is one of the things that causes confusion, because concrete likes vapor. Concrete really, really likes vapor. The higher the vapor in the concrete, the better. But floor coverings particularly don't like moisture. So you've got the concrete, which likes the moistures or vapor particularly, and then you've got the floor covering, which gets affected by so you're looking at, from the concrete industry versus the flooring industry, it's a very different problem. But this is from Bob Higgins here this is one of the pictures I took from his presentation. He's on the call now, so I'm sure he won't mind. But I think this is a very good presentation. This is a very good example that somebody can actually do this themselves. They can. So if you have 100% water, the air above that water will become saturated. If there's salts in the water, then that saturation will reduce. And you can experience this for anybody who has lived by the ocean or lived by a lake. You can see this exact phenomena, that if you live near a lake, this humidity is very high in the air. And if you live by the ocean, it's not, because of the salt. So similarly, if you use a calibration check plate, a calibration salts for any relative humidity probe, if anybody has used one of those, they will understand this analogy. But the calibration salts check, usually they use table salt, I think, which creates an RH of about 75%. So you're expecting the RH to be 75. using the salts, but the salts is water in a container. So the RH should be 100%, but it's not because of the salts. So similarly, if you look at this chart here, you can see the difference between moisture content based on the presence of alkalinity or salts. It's got sodium hydroxide and potassium hydroxide in the top one. And it's when you get above 90% RH that this causes a big problem, because if people only measure vapor and they decide they want to measure the high 90s, they have to know what moisture content is, or they only got one piece of the information. So yeah, so this Chris is just me putting to what it should be according to gravimetric testing. So right. This is, well, later on I will show you a chart from the VTT in Finland, that shows these different tests and how they relate to each other, and this will make more sense. But Chris, to your question, we expect about 4.5% moisture content at 90% RH. We expect about 4% moisture content at 83 to 85% RH. So the way to understand this, and it's important that it's understood correctly, because this is intended to show you that the condition of the moisture is okay. In other words, if you take this bottom line of this chart, that is concrete that has hydrated properly. It has cured effectively. And so there is less salts present because they have hydrated, they have become concrete. So this is what we're hoping for. This bottom line is what we're hoping for. And that's why we've lined these up. We're hoping that 4% will be an 85% RH, 83 to 85. We're hoping 4.5 will be 90. And if we get that, then we know it's good concrete, because there isn't alkalinity issues. So this is intended to measure both. If you measure one and assume the other, then this variable of the alkalinity will trip you up, or can trip you up at times. So when we've made our equipment for testing concrete, we've always included moisture content and vapor together when possible. There are some residential.
That's exactly what the audience wants to hear, because we're not scientists, and we start to look at the different components of this, and you get lost in the science very quickly. So we all look to sort of equipment that will help us to take the difficulty out of it and make it as simple as possible. And it sounds like that's where you've moved towards as a company. Yeah,
well, the whole idea is that moisture causes problems, and pH, alkalinity. So alkali moisture is your biggest concern. We don't see that there's only one way to test. What we feel is that you need to know what you're testing, because there's a misconception out there that when you measure the vapor, you're measuring the moisture. So if you imagine how much moisture concrete can hold, especially if it's a permeable concrete, it can hold a lot of moisture. And it is when the concrete is saturated, is the RH at 100%? The answer is no. If you look at this chart, you'll see that the RH in good concrete will saturate at about 5.5, probably 5.5%. It will be saturated, and possibly even up to 6% it can hold. So that's the problem, that it's saturated concrete that causes a lot of the problems, because you're trying to bond to something that is all the pores are already full of moisture. So there's no way for it to bond and to dry, for the moisture to dry. So let me just go on to the next slide here. This is another misconception in the industry, and I'm not sure where this comes from. Maybe Bob or William or will know the answer to it, or Clayton possibly. But I think it came from the calcium chloride test. The calcium chloride test measures the amount of vapor that can come out of the concrete if you create the right conditions. So by putting calcium chloride into the Petri dish, you're reducing the ambient humidity. And what that does is it draws moisture out of the concrete into the dish. And that is a vapor test. So you're measuring the amount of vapor that could come out of the concrete if the conditions were right. So, you know, from that, people have made an assumption that water vapor causes damage, which generally it doesn't. When you distill water, you do so to gain pure water. So the water vapor that comes off from distillation of water is pure water. What the contaminants get left behind. And so we have a similar situation with concrete in that when concrete is first placed, the salts are generally lighter than the aggregates. So what happens is the aggregate sinks to the bottom and the salts stay near the top. And then if vapor saturates, so if you get humidity, vapor saturating into a liquid water, then it can absorb those salts, and you can see the effects of that. But there's an assumption that the vapor is carrying salts, and that's incorrect. And it's important to know that it's incorrect because vapor pressure is tiny when compared to the bond strength of any modern adhesive. Similarly, hydrostatic pressure is also tiny compared to the bond strength of the idea that it's vapor or it's hydrostatic pressure that's creating blistering or other things in floor, other damage. The two things that are often blamed for floor failure is vapor pressure and hydrostatic pressure. And generally the strength of those pressures is too small to affect a good adhesive. So here I've done a thing about hydrostatic pressure. I put the toilet in there because that's the best example you can think of hydrostatic pressure. It's when you have the water table higher than the floor that you're installing on. So in a basement, it's possible to find on a ground floor, if you have like a hill coming down with water flowing down, it's possible, but it's rare. It's extremely rare. And because if you think of hydrostatic pressure as pushing water up through the concrete, there's an assumption when you see blistering in concrete, there's an assumption that that is caused by hydrostatic pressure. And I think, to be fair, for the most part, most people realize that now, and it's most people have moved on past that. But I hear a lot that people say, oh, vapor pressure, they see issues being caused by vapor pressure. And, you know, really, when you start to measure vapor pressure, it's so small that it's really not the cause of problems. So I don't know if you can see this whole slide, but this osmotic pressure is more commonly the cause of issues, especially in resilient flooring, especially in coatings, actually in concrete coatings as well. But basically what happens is this is sometimes called osmotic blistering. I think Peter Craig refers to it as osmotic blistering. I've heard it a few times. Yeah, so moisture problems can come from many sort of variations of moisture problems. You know, like if there's alkali moisture, it can break down an adhesive. If there's just too much water under a floating floor, it can create smells. There's this osmotic blistering is a major cause of failure that we see, especially in coatings or epoxies, as you say.
Can you describe osmotic? What is that?
Yes, certainly. So yeah, if people get this, it's helpful. So and this is going back just to school level science. Osmosis is the transportation of moisture. This is from my school, from an area of low chemical content into an area of high chemical content through a semi-permeable membrane. So basically moisture, if there is moisture present when the epoxy is put down, and there's two parts that are mixing. So the epoxy has two parts that are reacting with each other to create the finish that you need. And if there is moisture present during that phase of mixing between the two parts, then that moisture also reacts with both the parts, or at least one of them, and it creates a chemical byproduct, if you like. And that chemical stays underneath the floor. And so there's an osmotic difference between the chemical attracts water into that space through osmosis. So it brings moisture into that chemical through osmosis, and it brings it into a space which is under the floor covering, between the concrete and the floor covering, where there's no physical space for it. And as moisture cannot be compressed, it creates a really strong hydraulic or compressive pressure.
Which we would normally blame on hydrostatic pressure, for example.
Which would often be blamed on hydrostatic pressure, even though it couldn't be hydrostatic pressure or vapor pressure.
Yeah.
So it's a and actually the solution for it is to make sure that the surface of the concrete is dry enough so that the curing or the setting, depending if it's an adhesive or an epoxy, but so that curing can take place without creating a byproduct. And that's where fans are often used. So I'm just going to go on to this part, because there'll be a lot of questions from this. I can see from Bob's chat and others that there'll be a good bit of discussion. So I'll just quickly go through this. This was the VTT in Finland. They tested 13 different methods for measuring the moisture in concrete, different meters actually. And what's interesting is if you look at this chart, at the very bottom is 0 to 8%. So that's percentage moisture content by weight. And the first one here, we have the oven testing. Oops, so it's oven testing. So this is gravimetric. So for people who don't know what gravimetric is, it's the way that they measure moisture in wood or most building materials. Basically, you take a sample of the material you want to test to know the moisture content, you weigh it, then you place it in an oven, usually over 100 degrees Celsius, which is 270 something. Anyway, sorry, brain's not in gear. But anyway, and you boil off the water and then you reweigh it. So by doing that, sometimes they call it weigh, dry, weigh, because you have to go back and forth a few times. But when you see that, you can see on the bottom, they have at 4.5% moisture content with this sample. If you look at the Tramex concrete meter, it's very close. And above that, you have polished concrete. Do you see one of them has been abraded and the other one hasn't. And if you look at that, it just shows you the importance of preparation. If you're using a meter to measure the moisture, you have to treat it a little bit like the calcium chloride test, where you prepare the concrete, you make sure it's bare, you make sure you're testing on the same condition that you'll be installing the floor. And if you do that, it gives you a very good moisture content gauge, if you like. It's a very good meter for that. If I can see, yeah, there's one on the other side. Yeah, again, you can see this is at 5%.
So Andrew, the GAN meter, the second from top, because
yes,
it's got a long bar there between 4 and 7% is kind of inaccurate.
Yeah, that's the meter with the ball on the end of it. You know, the one with the ball, and there's a number of meters like that in the world. Even this Humi test is similar, but it's just off the scale. That's why you see this small line. But basically, they're called signal loss meters. So they're made. Our moisture encounter, our ME5 would be similar in the sense that they're made for repeatability of readings, and they're made for finding the moisture rather than a measurement like the concrete meters. But so anyway, if you treat it like a calcium chloride, in other words, you make sure the surface is abraded the way it should be. Sometimes they use a carborundum stone just to abrade an area for testing.
But makes that chart tells me that the Tramex is actually very accurate for what it's
it is. Yeah, it's now there's a whole variety of different screeds and everything else that you can get, but the majority of what you're testing with that meter is the moisture. So it's sending a signal from the surface down into the concrete, and you are measuring mostly the moisture, because it's an impedance test.
To what depth is it accurate?
About the first top inch of the concrete, which is where you're bonding to. So sometimes people say that, you have to measure deep into the concrete, and, that's fine. There's no harm to measure deeper into the concrete. But the majority of your testing should be around the bond line, because when there's issues.
Provided you don't have a hydrostatic pressure issue, you're fine to just deal with the top 1 inch.
Yeah, yes. Yeah, well, yeah. And there are cases where you can't. Like, for example, some of the residential flooring, they won't allow you to drill into the concrete. It's just not an option. And so the best you can do is measure from the surface down and then check the ambient conditions. So your second point is the ambient. Ideally you wanted it to be at between 70 and 80 degrees Fahrenheit or 20 degrees Celsius, and you want it to be 55% RH is the ideal ambient condition. So anything outside that is okay up to a certain point. But if you start to see ambient humidity either very low or very high, then that should be a big red flag for the need for more testing.
Which you show us that in a future slide, right?
Yeah, let me go on to. So this is just, I'll leave this for a second, so if anyone wants to pause on it and read it in future. But this was the abstract from that VTT test. Basically, they were looking for a way of testing bridges. So they were testing concrete bridges, and they did it in a laboratory test, which was actually closer to what a flooring. Normally, we expect a floor to be enclosed. We expect the roof on, the windows closed, everything else. So we expect it to be an indoor environment. And for that purpose, like you said, Chris, it is very accurate like that. Here's a close-up of one of their charts. There's also a chart they did on very old concrete, really, really old concrete, which is interesting because it was from a bridge where they were salting it every year. But if you look at this one, see the bottom test where it says, I can't, my Finnish is terrible, but cuvatus punitus. Yeah, cuvatus punitus. It's oven testing, so actual moisture content. So if you look at the bottom here, 5%, and then you look at the next chart up, it's 4.5%, and the meter is sort of matching it. But you see this calcium carbide, if you look at this to the left, this is reading just below 3%. So I'll quickly go over the calcium carbide. Most people on this call are never going to use it. But it's a flask it's the DIN standard, the German standard. And you're supposed to chisel, although some people drill samples, but you're meant to chisel so as not to dry out the sample, a piece of the concrete. And then you crush it into a powder and you put it in a flask. And then you add in calcium carbide, which reacts very violently with water. It's explosive material. And that reaction with the moisture that's in the concrete, that reaction creates pressure, and you measure the pressure, and that's how you measure the moisture content. What's interesting about the calcium carbide, just so people know, is that you mentioned, Chris, in the introduction that there's two types of moisture. There's vapor and there is liquid moisture. But there's actually, and this is something Bob and I were discussing recently, but there's actually three types of moisture, because there's absorbed moisture as well. And actually there's adsorbed absorbed and adsorbed moisture. So concrete has moisture within it, which is known as absorbed moisture. And then it has moisture that's attached to the aggregate or attached to the, and that's adsorbed. It's like droplets on the outside of an aggregate. So the calcium carbide test will not pick up that absorbed moisture. And that's why it reads about 2% usually moisture content lower than gravimetric. So it won't pick up the absorbed moisture that's in the concrete. And, you know, you can mimic that with gravimetric testing, with oven testing, by not boiling the moisture, the water. So you can, I think it's 60 degrees Celsius, and I'm not sure what it is in Fahrenheit, that they use for oven testing to mimic this calcium carbide. But anyway, as you can see, it reads about 2% lower than actual moisture content. So what I wanted to go through is we've sort of developed a probe, a concrete probe, which measures the moisture content. So the idea of that concrete probe is it works in the same hole that you're using for F2170. So speaking first of all to those who do F2170 testing, our recommendation is to keep doing it because it's for no other reason, you know, if only for the reason of following the standard. It's also a good thing because it's a standard test method. So if you're in the United States, I'm not sure about Canada, but sometimes you are doing 2170 testing. And actually our view is that 2170 will tell you in time about the alkalinity condition of the concrete, but that has yet to be proved in the field. So we're very hopeful on that. We will be able to combine 2170 with moisture content, and then you will know more about the concrete, about the alkalinity of the concrete. But initially what we have done is we've developed a probe. So this is our normal concrete meter, or this is our newest concrete meter, the digital one, that has the ambient, so you can see all the ambient humidity and temperature and everything, dew point and grains per pound are all displayed. So the top 3/4 of an inch, if you like, on that, it actually reads about an inch into the top of the concrete. And that's where you get your moisture map. So if you think about it, we supply moisture equipment to the roofing industry, the flooring industry, the EIFS, which is external insulation, all around the building envelope, they use meters, and they always do the same thing. There's usually 2 tests that are done together. So for anyone that's familiar with water damage, the water damage industry, the 2 tests are the pin meter and the non-destructive. So they basically use one to record numbers, and they do the other one to map the moisture condition. So it's something similar. This is a moisture map. And what you're trying to do is get enough readings to determine if there's any potential problems in the slab, and if it all is sort of similar within 0.5% moisture content, then you know there's not external problems. But if you do find areas where there's high moisture, that's the areas you mark to do further destructive testing if you can. So for commercial flooring particularly. So this is actually one I got from William's slide, where this is according to ASTM 2659. You're supposed to take between 3 and 5 readings in the same location and record the highest number. And then with that one location, you move to the next spot. I think according to 2659, the ASTM standard, you do 3 tests per 1,000 square feet and 5 for the first 1,000 square feet.
It is 3 to 5, but 5 is the better way to go because it doesn't take a whole lot of time to actually do that. So,
yeah, very good. Yeah. So this is with the app. So this chart on the right hand side is pulling numbers from here and giving you this psychrometric chart. That's what it is. So you can see the orange going out to the left is your dew point temperature. Your red going to the bottom is your temperature. And then the blue one in the middle is your relative humidity. That's a really fascinating chart. I won't go through it.
Andrew, can you go back to the last slide?
Yes.
Okay. we wind up from time to time when people are doing this testing, they're not actually getting the concrete ground down to do the testing correctly. So it's just as important as calcium chloride that you're actually testing the concrete. You're not testing sealers, you're not testing glues on top of it. So you've got to get that down to a 12-inch by 12-inch square. You grind the concrete down to the point that you get into open slab and then test it that way.
So this is the impedance probe. So this is designed to go into exactly the same hole that you drill for F2170. So people most interested in this will be those who are doing 2170, because it gives you a piece of data without any extra endeavor to get it. And it's exciting what this data is actually giving. We launched this product probably at a time where there was already 2170, there was already the impedance meter. And so we're giving, it's like adding one more piece of data. But what's interesting is you measure, the way this works is you push the meter on top of this box and it links up. And so it sends a signal from the bottom to the top. And it's so simple, but what that does is it tells you, like you said earlier on, Chris, if you've got a moisture issue, the two major sources of the moisture is from the air or from the concrete. You know, is it moisture that's coming up from the concrete that is going to build up over time? Or is it moisture coming from the air into the concrete, in which case you need to possibly correct the ambient conditions by either dehumidifier or heat or air movement or whatever combination works to get the right conditions. But when we use this probe, we expect it between 0.5% and 1% higher reading from within the concrete. So any more than 1% higher reading than the surface reading means that's a good indication of hydrostatic pressure. And if you get the opposite, where you get the surface being higher than the probe, that's a very good indication of dew point issues. And people need to know that dew point issues can happen at 3 o'clock or 4 o'clock in the morning. So it's not necessarily something you can test the air for at the time you're on the site. So, you know, you can get an idea if there's elevated ambient humidity, and you could say that that could be the cause of dew point, but mostly dew point issues happen. And dew point is when the surface of something drops below the dew point temperature. So dew point is a temperature. So if your room temperature was 70 degrees and your dew point was 60 degrees, that means any surface in that room that drops below 60 degrees is going to get condensation, possibly mold and other issues as a result. The easiest way to see it is if you have a glass of water with ice in it, you'll see the outside of the glass starts to bead up with water and it gets fully wet because the surface is below the dew point. So
at least we know when we're dealing with condensation on windows because you can see the droplets. But
that's
with
right.
Concrete, you can't see it forming. It just soaks straight in.
It gets absorbed. And the thing about dew point is, the important thing about it is the last thing you want to do is seal it, you know, because if you seal it, you're leaving nowhere for that water to go. Like you said, you know, if the concrete is sort of okay and you have a dew point issue, the concrete will absorb the extra moisture. It'll act like a sink. But if you seal that and then you have a dew point issue, you're just going to have a more slippy surface or whatever you would have, because it'll just sit on top of the sealer, whatever. So yeah, so this is a very simple way. Initially, the idea of this is to tell you whether the moisture is coming up or going down, and that's why we call it the determinator, because it determines the source of the moisture. But also, we're hoping in time that this sort of reading from here, if you imagine it's 1% higher than the surface, therefore the surface is at 4%, and then we expect this to be at about 5%. And what's interesting about that, for anybody if anyone's familiar with Australian standards, until recently the Australian standard was 5%. for moisture, and it was based on a test, an in situ test, something along these lines, not quite the same, but very similar.
5% at 40% depth, or the 3/4 inch?
It's a good question. I'm not sure if how they did the depth. So the 40% depth becomes important when you're measuring vapor, because the theory behind it, and possibly the fact behind it, I'm not certain, but the theory is that if you measure the vapor at this 40% thickness of the concrete, once you cover that up, that floor up, that vapor will be what is at the surface. And that's where it gets really interesting, because this 85% RH, if you imagine 85% RH being at the surface, that's your 10 degrees from dew point. And that's the bit that people probably won't get on this meeting. But 85% RH, if it's at the surface, is the same as 10 degrees from dew point. Because if you imagine for every degree Fahrenheit that you drop, the relative humidity goes up by 1.5%. So that means
this is where the science just leaves the understanding of the
yeah, and that's the problem, because if you think about it, that's how relative humidity testing was developed. It was developed as a way of making sure the concrete wasn't humidity saturated. In other words, that the moisture that was in the concrete was absorbed or adsorbed, and not free moisture, which would show up as a really high relative humidity number. So this thing of being 10 degrees from dew point and about the humidity, in other words, if you're below 85% RH in situ, it's presumed, quite reasonably presumed, that you will not have moisture problems in that concrete. Okay, there just won't be moisture there, because you'll be below the humidity saturation level. So that's the purpose of it. That's where 85% came from. And it was written into all the Scandinavian standards for many years. The problem we had in the United States, in my view, is that it became a competition between manufacturers to say, well, our product can go to 85. And then another one said, well, ours will go to 90. And another said, ours will go to, and I think at this stage, it's already gone past 100%. And the real problem as installers or as inspectors or as even flooring companies, the real problem there to understand is that we're measuring something beyond the ability of that test. That test will saturate at about 4.5% moisture content, or 5.5% moisture content. You would expect the humidity to be saturated. So if you want to go to 99% RH, it means you're using the wrong measurement. You should be looking at moisture, not vapor, because when the vapor is saturated, you don't know. Anyway, this is where it gets sciencey, but basically the alkalinity of concrete, in general, you can have humidity saturation above 93% RH. That means a slab at 99% RH is going to have less moisture than a saturated slab at 93%. And that's where the problems come. So I don't know, Chris, if that makes it clear.
To really truly understand it, you got to keep coming back and having these conversations, because unless you go to school to learn this stuff, it goes over my head, most people's heads, and it's part of the problem out there. Is it's too complicated to quickly, effectively, efficiently on site when it's pushed to the deadline. It's too complicated to take meaningful tests, and so a lot of people just ignore it and hope it just goes away. But I think your equipment is helping to simplify this. That's 90% of the problems would go away if we could just simplify the issue.
Yes. Yeah, and you'll see a huge reduction in problems if we start looking at moisture and vapor separately.
Yeah,
because
I love the conversation around dew point. It's always been around, it's just never really been front and center with the spotlight on it. Folks like Robert Higgins has done a great job bringing this to everyone's attention. I think it's got a lot of legs, that topic.
Actually, I'll tell you something. I think Bob is on here somewhere. I saw his name.
Here.
Great. Okay,
We
well,
are- we
I'll,
are tight for
I'll tell
time.
you something that I heard from my predecessor in Tramex was that they first started hearing about Dew Point from Bob. So that goes back, that's going back 30 years probably. He's been talking about Dew Point. So now it's becoming more understood in the mainstream, but certainly, yeah, it is worth understanding how because if you think about it, concrete is always probably about 2 degrees cooler than the air. And the reason for that is evaporative cooling. So if anyone wants to know what evaporative cooling is, it's basically the way I look at it, because it's simple. I have a simple mind, is the moisture needs energy to turn from a liquid to a vapor. And so whenever you have a surface where vapor is drying, where moisture is drying, it's using energy, which in the form of heat, to evaporate. And that it takes that heat out of the surface of something. So if you look at even a drywall where there's a patch of water on it, you'll see the temperature is cooler than the drywall where there's no moisture. And that's the basis of sort of infrared testing, if you like. So this meter, you can see on the meter, the first is the temperature, the second is the relative humidity, and the third one is your dew point. So in that case, we are now 7 degrees above dew point. So the dew point is 63 and the temperature in the room is 70. So it's a little bit high. The ambient conditions are a little bit high. I would say that having that ambient RH of 75 is a problem, and you need to correct that for the floor to be have the best chance of success. And correcting ambient humidity is easy. It's easy. The whole water damage industry is based on it. They rent out air movers really easily from places like Sunbelt and others. They'll deliver them to site, air movement, dehumidification, whatever is needed. The important thing is to know what you're doing. Don't just try to dry something out, because too much heat, too much dehumidification, too much air movement can cause problems. But if you understand what you're doing, and Chris, I mentioned to you before about Mickey Lee. Mickey Lee worked with Munters for many, many years. He's the author of the S500, which is the standard for drying buildings. And he did a lot of work on drying concrete, which I found very interesting. You might want to consider his input at some point.
Reaching out to him, yeah.
So the surface temperature, the only reason to check the surface temperature would be in an instant like this, where you're sort of close to the dew point. So if you're more than 10 degrees here from dew point, you can check the surface temperature if you want, but it should be where the temperature here is 70, the surface should be about 68. This is obviously a different piece of concrete, but so actually William's here as well, which is great. William was speaking earlier on. This is one of his specifications, just to show you what can be done. And I think how William mentioned that we should test properly abrading the concrete is important if you're using the meters like this. So you have all the different types of, so there's a multi-set adhesive, there's a sports spray.
We're dealing with acrylic adhesives, water-based adhesives, we're dealing with urethane adhesives, and we're dealing with epoxy adhesives.
So I don't know, Chris, how do you want to do this? Do you want to go to the questions now, or
is that your last slide?
I think so, yeah. I think that's pretty much what I wanted to cover.